All right, let's get started. Our attendance seems to be dropping each week. Not sure why that is, but it might just be that it's really cold out today. Oddly, we have still 300 people in the class between the two sections, so at least 300 that submit assignments. All right, so we've been talking about regression and various aspects of regression. The most recent thing we talked about was the bias-variance trade-off. This is the trade-off between when we're choosing a model, or rather a model family, there's always a trade-off between the variance that you get with that model family versus the bias that that model family introduces. So what does that mean? Bias is the limit on what the model family can represent. If you remember the graph of the fish, where the weight of the fish versus the length of the fish, it had sort of a curve to it. A linear function, a straight linear function, will not be able to accommodate that curve. That is bias. Bias is an aspect that even if you've had infinite amount of data, every model family will have bias in it. It's really a constraint of the model family, what it's able to represent. So even in the presence of infinite data. The other form of error that we get from models is called variance. And variance is just the error that comes from taking a small subsample of data compared to all the data that you could possibly get. So bias is with infinite data. Variance is because we only use a sample of data to train. So that's kind of the two major sources of error in a regression. Now there's this third source we did talk about, which was called irreducible error. This is just error that comes from the world. The weight of a fish given a set length is going to vary. There isn't going to be an exact number that comes with that. You can never predict that. You could never say, you could maybe predict the amount of difference between those fish weights, but you can never say, if you have 3 fish in your data set, one which was, all 3 which had a length of 10 centimeters, and one which was a weight of 10, another with 12, and another with 14, there's nothing you can do about that. That's just irreducible error. You can't get rid of it. So those are the forms of error. We talked a little bit about using cross-validation just to sort of get a feeling from where you can use cross-validation to sort of decide what model family is the best to use, just by looking at the error on cross-validation. That's a good way to do it if you have enough data. The book also talks about a couple other strategies that if you don't have enough data, you can use. They're actually fairly limited. It's basically, there's a number of strategies that basically count the parameters in your model family and penalize you according to those the number of parameters. They're not used very often. They're only when you have very little data and can't do cross-validation. So they're a little limited in their use cases. Okay, so I wanted to talk really quickly. I want to back up just a second to something we talked about with regression, which was the calibration plots. In the book, there's some examples of calibration plots. And again, just to remind you what a calibration plot is, it's basically the true value, the y value that we should be predicting, versus the actual predicted value. And if you, this is synthetic data. This isn't even a real, I never even did a real regression. I just created some data that shows these kind of patterns. So if you look at this is a really good regression. We're supposed to be predicting a value from 0 to 10. For any predicted value, we're right on that diagonal line where it says, the predicted value is really equal to the true value. Now there's some noise in the measurements here. I just put that in there so it was obvious that this is how regressions will come out. There will always be a little noise in your values. So this is a good calibration plot. Now let's look at a couple that just briefly that aren't so good. Here is a systematic overprediction as you get higher into the values. So what you see here is that we start overpredicting up at the top end. Now this could happen anywhere. It can cross over. You could be underpredicting at the lower end, overpredicting at the higher end, that sort of thing. So this is a bad thing. Generally, you won't see this kind of this sort of straightforward mistake. This could be caused by some outliers where we've sort of pulled the regression into an odd spot. But generally, if you have this sort of pattern, the regressor algorithm can actually usually get you on, sort of on target, because really it just has to tilt where the plane is here. So sans any outliers, it should do a better job at calibration than this generally. Here is another pretty common pattern where you have sort of a change in variance over the range of the predictions. So you're actually doing a really good job down here at the bottom and a somewhat poor job up at the top there. So this is not unusual. Typically at the ends you have less data and it's a harder thing to get the predictions right. So in this case maybe the data was much denser down at this end, so it spent a lot more basically minimizing the residual down at that lower end. And at the top end, it starts seeing a much higher residual because it didn't have as much data. It might be something that actually there is irreducible data here, or irreducible error that's just due to the actual data set. Like in the fish data set, this would actually be somewhat expected. You don't expect a big change in the lower values because fish that are 1 centimeter are very close to each other. Whereas fish that are 100 centimeters, you're going to have more variance. So some of this might be irreducible error, in which case can't do anything about it. But often you will see this where as you get up into the high ends, you'll get some increase in variance. And at the lower end, you'll get that same sort of thing where you get a little bit of an increase in variance. The last one I wanted to show was sort of this systematic skew that's sort of correlated to the value in some way. This certainly you don't want to see. I mean, you can't control a lot of these things. This is just what they're going to come out to be. But you should definitely know on this one, if you're going to use this sort of regressor, that there is a definite skew towards that top end. Like you start over-predicting quite a bit at the top end. So that's something you should watch for. And again, you're limited on what you can do. This is more of a tool to see how the regression's working. If you need to, maybe adjust parameters. If there's hyperparameters, you might be able to adjust. Do you need to look for outliers that might be causing some issues? If you do your regression and you have almost a perfect calibration plot, then you don't need to look for outliers. You don't need to go through and maybe add a bunch of regularization, that sort of thing. But if you have sort of these skews, you might want to look at other model families. If your model family can't support the kind of pattern that you have, often you'll get this kind of curved skew. Like if we looked at our fish, the residuals on our fish, we'd have an underprediction on one side and overprediction on the other side, so you get kind of an S curve there. So this is just some of the correlation plots that we talked about earlier, and like I said, I just wanted to show a couple of them so that you guys had seen some of the different things that could happen. These are used quite a bit, actually, when you're just trying to verify that there's some sanity to your regressor. Okay, so we're going to go on to another topic today. Actually, a bunch of topics. The first one I'm not going to go in depth on. It's about robust regression, And there is a blurb in the chapter on robust regression. But I want to mention what it is so that you guys could kind of, if you ever hear the term, you know what it's referring to. So robust regression is a process where, let's take it from a different angle. We know that there's an issue with outliers. So if we have a bunch of points that are kind of along some nice line, and then we have an outlier or an outlier, what we want to get is, this sort of pattern. That is the non-straightest straight line ever. You want a nice straight line that goes through your data. Now, if you have some outliers, these outliers will do something like this, where they force the line down quite a bit. And the reason they do that is because we're using a squared error. So the error on, if you look at, the prediction of this point versus if we extend this line up, we have to take the square of that guy, which is going to be huge, as opposed to taking the square of a bunch of, if we have to pay this cost for these multiple points, sure, we're going to pay some costs for those smaller errors, but you can have a lot of small errors that, sort of compensate for that giant error. So this is a real common thing that happens with outliers. So again, it's because we use a squared error that we're trying to minimize the squared error, and that's really our problem. So one solution to this is to do something called robust regression. And if we look at our error function, that's not our error function. Let's try this again. If we look at our error function, we're going to have a parabola sort of thing. So as we go up, we're going to have this giant jump in the error. You get the squared error here. Now this is the problem, is that an outlier, something that lies out here, is going to have this really large error. And that's the issue. We want to get rid of that somehow. So there's a bunch of different ways to do this, but the general concept is we're going to change the error function in some way. So we're not going to use a squared error anymore. We're going to use something else that makes more sense. The one we'll look at today is called the Huber's loss. And the Huber's loss is just tries to basically change the error function so that it doesn't, it sort of penalizes, or rather doesn't exaggerate these outliers. And so the easiest way you can do this is we can just select, let me go to a different color here. We can select some point, and we're going to go call that sigma, because we like to call everything sigma. We can select these 2 points, and after that we can say, well, we know that points outside that region, maybe we shouldn't penalize at a squared rate. Now we still want to, inside this region, we do want to have some penalties at the squared rate, because we really do things that are kind of close to the line, just barely off the line. We want a really small penalty. Things that do have sort of, that are not outliers but farther away from the line, we do want to penalize at a higher rate than those really near ones. So we do want to have some behavior that's sort of a squared behavior. But once we get past this sigma, we kind of think, maybe these are outliers. And so after that point, we're going to apply a linear loss. So we'll do that. So instead of having this, a point here, having this giant error right here, it gets this error down here, which is much more conservative. And so outliers don't have nearly the effect that they do on the original squared loss. So is there any questions on that? Does that make sense? All right, cool. So the downside of the robust regression is that we now have a loss function that isn't differentiable. So we can't just come along and do a minimization using our standard take the derivative set equal to 0. So we have to do something else. And there's a lot of math in the book that talks about how we get to this something else. But basically what we're going to do is another iterative process where we select an initial beta, and then we're going to apply this loss function using that beta and improve that beta over and over. And again, the book has the actual equations. It's for this specific loss. It's not that interesting because it's a very expensive process. So you can definitely do it for smaller data sets, thousands, maybe tens of thousands of data points. But if you start getting into really big data sets, the robust loss starts having a little more problem. Now you can actually use robust loss with things like stochastic gradient descent, in which case you can use a Huber's loss mechanism. In which case, stochastic gradient descent takes longer to converge in the first place, but it will let you use sort of an arbitrary loss function. So that definitely is some options to do robust loss. All right, so is there any questions on that? That's all I'm going to say about robust regression. Again, it's a technique for sort of eliminating outliers. A lot of research on it, but it's not used all that often. All right. All right, so now we're going to go on to a really big topic. And this is called generalized linear regression. Or often abbreviated GLM. And this is one of the workhorses that you will see all over the place. This is used extensively in real-world situations. It's one of the most powerful sort of things that we do, and it's very flexible, the things we can do. Is that a question? Sorry. This is supposed to be a model. It's a good question because I had the wrong acronym. Generalized linear model. And the reason it's a generalized linear model is because we're not going to be we're going to use regression to solve other distributions, to solve other problems. For example, we're going to use regression to solve a classification problem. And this is what makes it really powerful. You can use regression to solve other types of problems. And more specifically, you can basically choose a distribution, a probabilistic distribution, that fits the problem you're working on, and then use regression to solve that problem with that particular distribution. So we're going to look at some examples of this, but first we're going to motivate how this works. So if you remember, when we did linear regression, we did something like this, where the prediction was equal to some linear combination of beta and x plus some noise factor. This is sort of the formulation we came up with. Now, this noise, we just assumed it was some normal with some unknown variance. Now, we don't have to assume that, but for this discussion, that's one of the ways we can sort of think about modeling linear regression. Now, just to motivate GLM, you can take this, if this is a normal, then you can look at this in two ways. You can say that y is some value of this plus a normal, or you can say that y is actually a random variable that follows the distribution that's a normal with x transpose beta being the mean of that distribution. So that's, we haven't done anything there. There's no magic there. We just push the mean into the normal by adding it to the normal, subtracting it from the outside. But this sort of motivates the power of GLMs. What you can think of this is that this parameter, that x transpose beta, is actually the parameter of the normal. So we're going to say that y is distributed according to a normal, but the parameter of that normal is predicted via a regression. So every single set of x's is going to have a different mean of that parameter, or a different mean because we're going to predict that mean parameter. And that's where the power is. Every different x gets a different parameter setting for the normal, and y is then going to follow that distribution. So and that's a key point. This is something I don't think they emphasize enough in the book, that for every different x, we get a different parameterization of the normal. So for one x, maybe we get a mean of 0.1. For another x, we get a mean of 0.5. For another x, we get a mean of 239. So we're actually changing the mean of that y value each time. So is that a question in the back or a stretching? I think that was a stretching. All right, so any questions on that? Yeah, so no, we don't get a different b vector. We have a single beta vector. But the x changes for every single one. So another way to think about this is sort of the yi follows the normal of the xi beta and then some sigma squared. So if you look at sort of a graph of this, if this is your predicted y, this is hard to draw, so I don't know if this will help you understand. And this is your xb. This sort of says, you know, there's a normal that is this. I kind of want to draw a normal like this, where there's kind of this. Sorry, this is actually going to be just x, some x. Where it's actually the parameter at each of these spots has actually changed. The mean has moved up in that case. But we're still looking at a normal around this mean parameter. Does that make sense? It's a hard thing to draw and conceptualize. But this is an important idea that you're actually going to predict. We're going to use regression to predict a parameter. And then that parameter is used to get the final y value. Any questions on that? Yeah, it's a fuzzy concept. It took me a couple times. I certainly didn't understand it in my first ML class, which I guess means there's going to be some of you that don't understand it in this ML class. But it is a very powerful technique. And the reason it's a powerful technique, question? Sorry, this was a let's just say there's some x, and then this would be sort of the x beta, the normal, and then the y prediction is going to follow this this sort of normal. I'm trying to draw a 3D graph in a 2D piece of paper there. So it's hard to draw this, but really this, as x goes, changes, the mean of this distribution for y is actually changing. So far, it's not at all. So far, this is exactly the formulation we had with linear regression. And in the end, when you predict y, you just predict the mean, because that's going to get that's your maximum likelihood. But we're going to take it a step farther, is where this is going to go. The normal motivates it. Looking at it in this probabilistic framework motivates it. But we are going to go past that to do other things, which is what we're going to do right now. So briefly, actually this isn't brief, this is the main motivation of this. Let's say we wanted to do classification. Now classification is, y is going to take the value, is going to take either a 0 or a 1 value. Now that is a lot like a Bernoulli distribution. So we can model this as where y is some sample of a Bernoulli. And so now instead of using a normal, saying that the prediction is based on a normal, we're going to substitute in a Bernoulli. So you're going to have some y follows a, well, I'm rewriting the thing right above it. Bernoullis are parameterized by a single parameter, which is the probability that you sample a 1, and then the 1 minus is the, 1 minus that parameter is the probability you sample a 0. So there's a single parameter here, and we're going to model that using a regression. Now I'm going to put some weird question marks here because we're going to have to do something special. But essentially, we're going to use regression to model that parameter. And now again, for each different value of x, we're going to get a different value of xb, which means that as x changes, actually the probability of getting a 0 versus a 1 can change. And that is the key here, that as this parameter, we're predicting this parameter, and then that leads to the actual prediction. So why did I put those question marks there? Well, a Bernoulli is parameterized by some theta, and that theta is constrained on the range. Theta can only go from 0 to 1. But when we do regression, we have a value that will go from negative infinity to infinity. So that's a problem. Now you can't just say, okay, anything outside of 0 and 1, I'm going to call it 0 or 1. You can't just clip it. That would be a terrible thing. Not only would it not be differentiable to actually minimize it, but you'd have this huge range of predictions that would just get clipped at 0 or 1. So you don't want to do anything like that. So what we end up doing is we create something called a link function. It's going to be, this is a term that will come up again. The link function is some sort of function that is going to map from negative infinity to infinity and map it into the range that we need to have. Now with a normal, we didn't need a link function because the mean of a normal has a range of negative infinity to infinity. Any mean's okay. I mean, negative infinity isn't okay, infinity isn't okay, but as long as you're not actually at the edges, you're just fine. The mean can be anything. With Bernoulli, that's not true. So we use this link function to translate from that really big space down to the constrained space of 0, 1. And the way this is typically written is, that's a terrible G. It's written kind of backwards, but this is historically how we write it, is that the link function links some theta, and theta is going to be the thing that has a constrained range. equal to the X transpose B value that we're predicting. Now, there are many different distributions that we can use with this. We're going to talk about just a couple. And there are many different link functions that will actually work. So we're going to talk about the most popular link functions. But a link function really only needs two things. It needs to do the translation to the correct range, and it needs to be differentiable in order to make solving these easy. If it's not differentiable, all of a sudden we're in a situation where we can't actually minimize. If it doesn't map to the right range, obviously there's going to be some problem there. So those are really the constraints on the link function. So for the Bernoulli, what we're going to do is, this is actually going to be, just to rewrite this, there will be some G inverse X transpose beta. That is the the inverse of the link function. So if this is the link function, then theta is equal to G inverse. Actually, there's a third criterion that it has to be monotonic because we have to be able to take the inverse. That's actually pretty important. So you get this sort of situation where the theta, that is your parameter you need to learn, is the inverse of the link function with the X transpose beta as the input. So let's talk about this Bernoulli. We're going to go on. And the Bernoulli is, oh, sorry, go ahead. What theta is? Theta is the parameter of the distribution. So like for a normal, the parameter is the mean. We assume there's only one parameter. You're only going to use this for things that have a single parameter. So you'll ignore sigma. But for the normal, we have one parameter, which is the mean of the distribution. For a Bernoulli, you have one parameter, which is the probability of sampling a 1 versus a 0. So that theta has a range of 0, 1. If it's 1, then you're always going to sample a 1 from that distribution. If it's 0, you're always going to sample a 0. If it's 0.5, you'll sample with equal probability. For a Poisson is another one that we look at where there's a single parameter that controls. A Poisson distribution is basically a distribution over counts. So lower counts generally happen more often than higher counts in a Poisson distribution. And then there's a parameter that kind of controls, is everything kind of at the front or is it kind of a long-tailed sort of thing. So that's what the theta is. It's the parameter of the distribution we're using, we're modeling. Does that make sense? Okay, cool. Okay, so when we use the Bernoulli, we call it logistic regression. This is the term that is used to describe modeling a Bernoulli, basically doing a classification problem using regression. Now remember, we're going to be doing classification because we're going to be predicting a 0 or 1 sort of thing, but we're going to use regression to do that. And that's why it's called logistic regression instead of logistic classification. Just to, if we're using the Bernoulli, we're going to predict a 1 with probability theta and a 0 with probability 1 minus theta. So the link function that we're going to use is we're going to look at the log of the ratio of predicting a 1, given our theta parameter, over predicting a 0. This is often called the log odds. That's what the description of this particular function is, just because it's the odds of 1 versus 0. Now, we know that the probability of predicting a 1 is equal to theta, and the probability of predicting a 0 is equal to 1 minus theta. So this becomes log of theta 1 minus theta. And that's actually the link function that we're going to use. So g of theta is going to equal log theta 1 minus theta, which we're going to set equal to x transpose beta, because that's what we want our link function to do. So now, given this, we can check that it actually does map 0 to 1, independent of, if x beta, it'll take an x beta that goes from infinity to negative infinity, or negative infinity to infinity, and it'll form a 0 to 1 range on the theta. So once we have this link function, we can actually take the inverse of this, and then we can use maximum likelihood to predict the values that we need for beta. So specifically, we can say the probability of y being 1, given our x value, is equal to the exponential over 1 plus. So it's the exponential of x transpose beta over 1 plus x transpose beta. Which, by the way, this is actually what theta is, because remember, theta is the probability of x being 1. Now, the probability of y being 1. The probability of y being 0, given some x, is just going to be 1 plus e to the x transpose beta. Basically, you just put in 1 minus theta. You move around all the stuff to get the inverse correct, and you get back this. So now we can estimate our beta using this information, and then once we have our beta, we can actually get the posterior probability. This is the posterior. So if we had a beta, if we learned a beta, now we know for any prediction what the probability of it being a 1, predicting a 1 versus predicting a 0 is, which is exactly what we want. We've transformed regression into a classification. Is it 1 or is it 0? Okay, are there questions on that? Okay, cool. I might run out of stuff today. I'm apparently going way faster than I'm supposed to be. Okay, so we still need to do the maximum likelihood to find the correct beta. So we figured out the formulas to actually, once we have the beta, to figure out what the prediction is. That's not a problem. But we want to be able to do the maximum likelihood, which means we have to find the formulation that we can take the gradient of, differentiate, set equal to 0, and then maximize. So what we need for that is the log likelihood. Whenever we want to figure out our maximum likelihood, we take the log likelihood and we maximize, or equivalently, we take the negative log likelihood, which is how it's almost always described, and we minimize. Now the log likelihood is parameterized by beta, because that's what we're going to learn. And it's going to be a sum over some error function. And this is where things start to get a little complicated. The formulations are in the book. I'm going to try to give you kind of a feel for it, but I'm not going to go through every step of the math. David often would go through all of the math, and for some people that makes, that helps quite a bit to see every single step of the math. But for a lot of people, I think seeing every step of that math while we're in class and you can't like think about it from step to step isn't that useful. So a lot of times I'll skip the math. If you guys are interested in it, come and talk to me afterwards. Or, like I said, the book often has the math in quite a bit of detail. But the loss we're going to use is we're going to use a mathematical trick here. Basically, when we have an input label that is a 1, we need to use one particular loss function. But when we have a 0, you have a different loss. Because remember, it's theta versus 1 minus theta. So we need a way to take both of those things into account in some fashion that we can still differentiate. So we use something called an indicator function. An indicator function is just a function where it is 0. It's 1 when the condition is true. So this is some condition, and it's 0 otherwise. So we kind of saw this when we were talking about EM for clustering, where we used a trick kind of like this, but the deltas were like an indicator function of whether something was in a cluster or not. This is a similar kind of concept, but it's used in a different way to be able to concisely write the loss here. So if we have this loss, the loss is actually going to be, basically you're going to take these equations and you're going to push, we're talking about the log loss, so we're going to push that log through everything. And then we're going to take this indicator function to basically switch between whether we're talking about a positive or a negative example. And if we do a bunch of transformations, we actually end up with this for our loss. E to the x transpose of, that's a little tiny beta. So that's the formulation we're going to use for the loss. Now what we do with that is anytime we have a loss and you want to find the maximum likelihood, you take the derivative and you set it equal to 0. And then 50% of the time you can't take the derivative for some reason and you have to do something else. But anytime you have a loss, you should really, as a knee-jerk reaction, take derivative set to 0. So now we're going to do a transformation. And that transformation is going to make the derivative, push the derivative into a form that's much more usable. We'll be able to get rid of this indicator function and have something that just works without that indicator function. And the transformation we're going to do is we're going to transform y into a new y hat. And all we're going to do is y hat I is going to be 2 times yi minus 1. And we actually have seen this before. If we needed to translate from 0, 1 to negative 1, 1 for, say, an SVM, you could use this sort of transformation. So if y is equal to 0, y hat is equal to 1. And if negative 1. And if y is equal to 1, y hat is equal to 1. So all we did is translate, change the range here. Now once we change the range, things become a lot easier. Do I actually have the differential? No, I never did the differential here. So given that, we can rewrite the loss, the negative log loss, to be y hat I plus 1 over 2 xi transpose beta minus log 1 plus E xi transpose beta. And you notice we got rid of that, that indicator function there. And then we can multiply this all out, and we end up actually with the log of two terms, one of which is e to the negative y1 plus 1 over 2 x transpose IB. Now I'm not sure if this x should be up into the e. I don't believe it is. 1 minus y over 2 x transpose beta. The reason we translated to -1 is you can see there's a nice little trick here that if yi is -1, this comes out to be 0. If it's 1, it comes out to be 2, and then you divide by 2, and the whole thing comes out to -1. On this side, if you have a 1, this comes out to be 0. If you have a -1, this comes out to -2 divided by 2, and so you get a -1 on that side. So it sort of acts as a switch. When your two values are negative y and y, you sort of get either this side of the loss or this side of the loss. Now I swear I'm missing a page of notes here. We could talk about the loss here, sort of the shape of the loss. And this is kind of going back. Remember when we did classification originally, we talked about the shape of the loss. Whereas if this was our x transpose beta, our loss was, when we did SVMs, we used a hinge loss. So our loss would have been for y equals 1, our loss would have looked something like this. So we want to sort of do the same thing here, is we want to have a loss that kind of has that same shape. And it turns out that the logistic loss, which is what this loss function is called, has a very similar shape. It kind of comes down, let me draw it in a different color. It kind of comes down linearly, has a little bit of a curve there, and then straightens out. So it doesn't have a hard corner like the hinge loss does, the loss we use for SVM. It has sort of a more curved structure there. But it has a very similar concept-wise. Like in one area of the regime of the values, you get basically no loss. You're predicting the thing correctly. And in the other area, you get kind of a linear loss. And that, if you do y equals 0, it actually just flips the direction of this. So the loss becomes, comes this way for y equals 0. And this is the loss for y equals 1. Okay, so are there any questions about that? So we take the derivative of that, we'd set it equal to 0, and then we'd be able to maximize, or rather minimize, because we put the negative on there, that particular expression. I'm not going to go through the derivation of that derivative. I'm not actually sure why I'm not, but it's not in my notes for some reason. I thought I was going to do it, but we're going to skip it. It should be in the book. Also, if you're going to use this, you're not going to go and actually do the math. There are going to be logistic regression algorithms that already exist. That won't always be true because you can use basically any single parameter distribution, probabilistic distribution you want. You can use you can use generalized linear models for that particular distribution. So some of them, if you want to use them, you might have to work them out yourself or find a reference. But for all the common ones, they're going to be available in, say, Python through like sklearn, or in R through, actually, there's a GLM. So there's going to be, these will exist. The other comment is that link function we looked at is not the only link function that you can use for logistic regression. There are other ones. The most straightforward ones are just sort of scalings, but have sort of the same behavior. But there are actually some link functions that sort of give you a skew towards either positive or negative. And those are sometimes useful. I've used them before for various distributions, and they worked a little bit better. But it's fairly rare that you end up using a link function that isn't symmetrical for that particular problem. So we're going to look at two other distributions. One of them is going to be the multi-class logistic regression. Multi-class logistic regression. This is the same thing as logistic regression. It's just for multiple classes. Instead of having a binary 0 or 1, you're going to predict an integer value that goes from 0 to sort of k. So you can think of it as a roll of a dice that has k sides. And you're going to, each one of those k sides will have some probability of occurring. So the probability of your y equal to some value, which we'll say small k, given all of your thetas, there's going to be multiple thetas, is going to be theta k. Now, there is a constraint here that all of your thetas have to add up to 0, because this is the probability, the theta k is the probability of it coming up with that value k when you take a sample. So if you have 3 classes and your thetas are 0.1, 0.1, and 0.8, the probability of sampling the first class is 0.1, the probability of the second class is 0.1, and the probability of the third class is 0.8. But those thetas always have to add together. So the way we deal with that is we say that the very last class, and we're going to number these from, we're going to call the classes 0 to k minus 1. So class k minus 1, given theta, is going to be equal to 1 minus the summation of I equals 0 to k minus 1 of theta I. So again, you're just, because they all have to add to 1, you take all the thetas up to k minus 1 and you subtract them from 1, and that'll give you the last, basically the probability of the last class. This is pretty standard. There's no magic there. So if we take the, we have to have a link function again that's going to map these from into 0 to 1. So we're going to use something very similar to the to what we've already used for logistic regression. So the probability that y equals 0, we'll just look at the first case here, given an x, is going to be equal to e to the x transpose beta 0 over a normalizing factor, which is 1 plus, let's see, this is k minus 2, I equals 0. This should be k minus 2 up here also. Theta I. So basically, you add up all the thetas, you add up the 1, you add it to 1, and that's your normalizing factor. So basically, this is just like the softmax that we looked at earlier, where it's some value over a normalizing factor so that all those values add up to 1. P of y equals 1 is, given x, is going to be the same thing, except you're going to change the beta to be beta 1, and then it'll be the same thing on the bottom. We're just going to have that normalizing factor. Now, because this has that oddity where it's the 1 minus whatever, we have to have that same thing reflected in our link function. So the probability of y equals to k minus 1, lowercase k minus 1, given our x's, is going to be equal to 1 over our normalizing factor. Summation of theta I equals 0 to k minus 2. So those give you sort of the probability of the different classes given your set of betas. And again, beta, the set of thetas, the set of betas are going to be equal to some beta 0 up to beta k minus 1. So you're actually going to be learning a bunch of betas, one for each class. And that beta will control the probability, the amount of probability mass that goes to each class. Yeah, I did. Good catch. It's I equals 0. We're just adding together all those theta values. Oh, and it's beta, not theta. It is, no, I have this totally wrong. Okay, this normalizing factor is x transpose beta I. So there's an x transpose there because we want to make sure that all of these terms add up to 1. So we take each of the terms, we add them all up, and with this term has a 1, so we just add them all up. So I apologize for that. It's a bad job doing my copying. So questions on that? Then you work through there's going to be a bunch of math to find the loss function. Once you have the loss function, you're going to minimize it, and it's just going to spit out these values. Once you get all the betas, it's really easy to do the prediction for what the probabilities are of each of the classes. Questions on that? All right, the last one we're going to look at is the Poisson distribution. And the Poisson distribution is a distribution over counts. So the probability of it has a range. It's a discrete distribution, and it's going to basically, there's a probability of seeing 0, there's a probability of seeing 1, 2, 3, 4, all the way out to infinity. So each of the integers get the positive integers get some probability of coming up with the Poisson distribution. So this is really useful for modeling something like the number of likes on a post. If you were to just model the number of likes on a post using, say, a straight regression, it's going to fail horribly. You're going to find, these Poisson distributions counts are often long-tailed, but they're sort of this, they sort of have a shape of something like this, where I've just sort of taken the, this is 0, 1, 2, out to infinity somewhere. If you did a normal regression for that, not only would you have the problem that it would go into negatives somehow, but it would have, you'd have to try to use some sort of linear function to do that, and it would be completely, kind of wacko. So it doesn't work to do counts with linear functions, but if we use the generalized linear model, all of a sudden we can do these things in a pretty nice form. The probability of y taking a value of some k with a Poisson distribution given some parameterization, is actually the theta to the kth, e to the negative theta, and then there's a normalization factor of k factorial. Theta has got to be greater than 0. And from that, we can come up with a link function, which is actually a really simple link function. Of log theta is equal to x transpose beta. And then once we work through the math and we were to find our beta, we get back to the original prediction. So the prediction that y equals k given some x input is going to be this kind of funky thing, which is e to the k x transpose beta e to the negative e to the x transpose beta over k factorial. Yeah, there's this e to the e sort of thing going on there, which is a little strange. But that's going to be the probability once we find beta. Now we haven't written out how to find beta here. Again, you take the link function, you push through all the math, you'll get something to maximize after you generate a loss. That math gets fairly complicated to write out. I mean, logically, there's no complications. It's just very long to write out all those transformations. So you end up, if you want to do this, you're going to use a package to do this. And if you have a situation where you do have counts, anything where you're talking about number of likes, number of views, number of anything, this is the thing that you should be using. Okay, any questions on that? Okay, so for one last point is that for GLMs, it no longer makes sense to talk about the squared error of something. So normally when we talked about sort of the error that we incur, we would do something like the squared error, which would be y minus x transpose beta squared. That's sort of our typical error of our regression. And then we usually took the mean of that, so we took it off over all the data points and got a mean squared error. This doesn't make sense for GLM because that's not what we're minimizing. So it doesn't make sense to use that. So instead we use something called deviance. That's a D, not a P. Deviance is just a different measure of sort of the error of a GLM. And the deviance of some data point is just equal to -2 log of the probability of yi given the xi and our beta parameterization. This is actually, we'll put a hat on it just because it's the beta that we found when we did the minimization. So it's an estimate of the true beta. So that's a different way to look at the sort of error function. Now, for linear regression, we actually, if we were to plug in the deviance for linear regression, we actually get something that looks kind of like this. Xi transpose, I'm not sure why this changed order, but and again, this is if we assume that the probability distribution is a normal, then the deviance of that normal, which is what we use for logistic regression, linear regression, comes out to be this. And so you see that it's it's the same thing. It's sort of a squared error. There's this constant k, which is all the junk that comes from sort of the normalizing factor of a normal. And then there's this sigma squared, which is sort of the unknown but constant variance of our estimate. So this does give you, it just shows that the deviance kind of has the same meaning, although it's been scaled and shifted. It has the same sort of meaning as the squared error does. So any questions on that? Let's see. I don't want to get into that. There is one thing I wanted to talk about. We talked about this. This is a topic that just is going to come up. It's probably something we should have talked about way back when we were doing classification. But the sort of when you're doing classification, and we talk about it now simply because we just did logistic regression, which is a form of classification. And specifically, it's binary classification. When you do classification with something like logistic regression, or say Bayes, naive Bayes, what you're going to get back is a probability distribution. And when we did classification previously, we just sort of said, if we got a probability that went from 0 to 1 of something being positive, we just sort of said, oh, well, we're just going to call everything greater than 0.5 as a positive, everything less than a 0.5 as a negative. That works, but it may not be optimal for your particular task. And so we kind of want to be able to look at some diagnostic plots and look at the trade-off. We could instead say that everything greater than 0.1 is a positive, and everything less than 0.1 comes back as a negative. Now that's going to trade off how many mistakes you make of calling negatives positives and positives negatives by moving that parameter around. So I want to look at a couple just quick diagnostic plots that we would use to kind of look at these things. Again, this is synthetic data, so it's just kind of distributions that I kind of generated to look at. I didn't actually do the logistic regression. But again, logistic regression is going to give you back values of 0, 1. What I did is, first of all, I kind of made some fake distributions of the predictions. And then I took I bucketed them and made a histogram of these. And I separated them according to the negative class and the positive class in this case. This is a common thing to draw. It's going to show you if you're actually learning anything. The more that these two distributions overlap, the worse you're doing on really learning the classification. So here we actually see that we get two sort of bumps. They're not quite normal, but they're sort of normal-ish, and they're fairly separate. You can see the dark blue area is sort of the overlap. But otherwise, you have the blue and the green that are fairly distinct. Now, we can move what we call a positive prediction versus a negative prediction by changing that threshold. So logistic regression is going to return an actual probability, 0.7, and then we can call everything with probability greater than 0.7 a positive, or less than 0.7 a negative. So if we adjust these, I drew in a couple lines here of different thresholds. And we can actually see different accuracies as we move that threshold around. And we'd expect pretty much, you kind of want to choose the one that has sort of the same amount of probability mass on each side. So you kind of even out the mistakes. That's sort of the optimal best accuracy you can get, but it might not be the best thing for your task. So if you want to look at this another way, is you can make some trade-offs. Depending on your application, it might be more important for you to make sure that you don't have false positives, or it might be more important to make sure that you get all of your, as many of your positives correct versus ignoring your negatives. So you can kind of trade these off by moving these thresholds around. And one way to look at this is called an ROC curve, or a receiver operating characteristic. They're actually developed back in World War II for evaluating sort of the parameters of radar. And what these really show you is sort of the trade-off of false positive rates versus true positive rates. So as you move the threshold from 0 to 1, you're sort of going to be increasing the false positive rates, but also increasing the true positive rates. And so a ROC curve can kind of show you this sort of curve. The higher you go into the corner, the better your regression probably is. Now, in the end, you're going to have to choose a threshold. So when you use your actual regression that you did, you'll have to choose a threshold. But in general, when you look to see how good your regression is, you can sort of look over the whole curve and kind of get a feel for how well you're doing that regression. So in this case, they often use the ROC area under the curve, AUC. Often just, if you hear AUC, it's often the ROC AUC. People abbreviate that quite a bit. And they often look at just the area under the curve, which is 0.96 for this one. The other way that you can look at things is something called a precision recall curve. A precision recall curve, again, we're moving a parameter, that parameter of what we call a negative versus a positive. And you could translate from ROC to precision recall. They go back and forth. They have sort of similar information in them. But the precision recall is telling you a different thing. It's basically saying, as you move the parameter back and forth of what you call a positive, you can trade off recall, which is the fraction of positives that you actually called positive. So as you move your parameter, you're going to call more and more things positive. So the recall is the fraction that you're actually calling positive. The fraction of the positives that you called positives. And the precision is, of all the things you called positives, which means that you'll have some true positives and some false negatives, because you'll call those positives, what was your accuracy on that set? So if you need something, the way that you kind of use these is, if you need something that is really, really accurate, but you're going to miss some of the positives sometimes, you use something over on this left end. So this is saying that you're going to get things correct almost all the time. If you call something positive, it is positive. But you're going to miss a lot of the positives. You're going to call a lot of positives negatives. If you're on the other side, you're going to have a lot less, you're going to cover more of the positives, but your accuracy is going to drop. So actually in this one, it's going to drop to, because this was a non-skewed data set, if you call everything positive, you're going to have a 50% accuracy, because you're just going to call everything positive. Now, when you get a skewed distribution, that's when things start getting kind of more interesting. So in this case, we had 19 negatives per 1 positive. So what you see here is there's a lot more negatives in the data set. You have the distribution here of positives, but there's so few of them that it's really not showing up. And this is not an uncommon thing. 19 to 1 is actually not a very big skew. Tens of thousands to 1 is actually a really common skew when you start looking at, say, fraud. The vast majority of things that happen in financial aren't fraud, but there are occasional fraud. And you want to sort of find those fraud ones without having too much of a false positive rate. The ROC curve doesn't look a lot different. I'm not sure if that was a bug in my ROC curves. I'm suspecting it is. So probably ignore this ROC curve. But the precision recall curve is where it gets kind of interesting. Now you can actually see there's a pretty strong trade-off. If you need high accuracy, you have to come really over to this left side. If you are okay with sort of middle of the line accuracy. So like here, if we get half of the positives, we're actually going to get about 60% accuracy. So depending on what you're, if you're doing a medical application, it might be really important to see all of the positives to never miss anything. Like you never want to miss somebody having cancer. So you might skew it far to the right here. Now your accuracy will go down. You'll say people have cancer when they don't, but maybe that's better than saying they don't have cancer when they do. It just depends on what your view is. Or maybe you've got to do something where it's going to be very costly to call something positive when it isn't, in which case you'd skew it way to the left. So these are kind of the diagnostic plots you use for classification. I think in homework 7 we're going to have you draw some of these, at least the distributions, to take a look at sort of how your GLM is sort of splitting the data. So unless there's questions, we're a minute over, so you're welcome to go.